Okay, so I hope you had a good sleep last night, right? I am going to just give a quick revision of what we have done till now after test 1, right? So, as you know, the syllabus is after test, first midsum examination, right? So, I think we started with 2 variable functions, and from there until last lecture yesterday. Okay, so let me start. Okay, so I am using the same slide which probably you will be using. This is the last slide that we had. I may try to do 1 or 2 more examples, at some point if time permits. But anyway, so we started with multivariable calculus. Means when functions are defined from r raised to power n to r. Okay, so that is n input, 1 output. Okay, and but I mean, since the theory is almost similar, except the visualization is sometimes different basically. So we focus on the case n is equal to 2. So basically from plane r square to r. Okay, those kind of functions. And by the way, what is Rn or r square? I think you will learn in some of your other math courses such as linear algebra that r raised to n is nothing but a vector space. Vector space means if you can play with vectors, very loosely speaking. You take 2 vectors, add them, you are in the set. Take a vector, scale it, you are in the set. Okay, so those kind of properties holds. That's a vector space. Okay, and it's very important actually. So we are looking at only n is equal to 2 case. So for functions from r square to r. So whenever we define a function, as you know, we can find their domain and range, right? The usual question that you ask in the single variable calculus, right? The domain and range, right? So for example, in this case, if the for this function here, range you can determine by looking at if the function is square root of 9 minus x square minus y square, so how it will look like, right? You can find the domain and range. And of course the plotting, you can look at it using Wolfram alpha. So that is really easy thing to do. You can also look at 3 variable functions. I gave you just one example. Then we talked about, since 2 variable function is nothing but a surface. Okay, so there are what we call local level curves, which will actually, it is easy to actually visualize the surface using the level curves. So contour plots and level curves. Then we talked about limit of a 2 variable function. So definition is exactly same. Limit of a 2 variable function f of x comma y is L. If for every epsilon positive there exists delta positive, such that distance between, so as long as distance between generic point x comma y and the point where the limit is approaching is less than delta. Now this distance here, normally we take Euclidean distance, but otherwise you can take any distance. Okay, that works in r square. Okay, as long as xy, the generic point, approaches towards a comma b, means when this distance is less than delta, right? So for every epsilon positive there exists delta positive, such that absolute value of f of xy minus L is less than epsilon. Okay, whenever distance between these 2 points is less than delta. Now why this is single mod? Because here the distance on the real line is mod of x minus y, right? Distance between 2 point x comma y is mod of x minus y, right? So this signifies the distance between image of the generic point and the fixed point L. That means image lies in the neighborhood of, you see, at the neighborhood of capital L, right? As long as this happens, the limit exists, right? Now, I mean, doing this definition is fairly straightforward, right? You can write it now. But now the important thing is that if I have to show that the limit exists, I should be able to show that the generic point x comma y in the neighborhood of a comma b, which is kind of a circular disk, right? The generic point x comma y approaches towards a comma b in any manner from any path, okay, if the limit has to exist, right? So in the single variable calculus it was only left hand limit, right hand limit. Here it is from any direction actually, right? So because it may happen that your generic point is here, so you are approaching like this, or right, or by some curve, whatever, you know, some way you are approaching towards point a comma b, right? And then the limit, the value should be same, right? So then the limit exists, right? Now if I have to show that a limit does not exist, it's very easy. Just find two paths for which the limit is different, and then you are done, right? To show that limit does not exist is a very straightforward thing. To show that limit exists, you try a couple of different paths, and if you are getting the same limit, then you suspect the limit is whatever you are getting, and then you try to prove it using epsilon delta. That is a summary of what you should know. Okay, I think still somebody was asking this question yesterday, right? So, but that's really simple, because here you have to use some sort of inequality, essentially involving sign, right? Okay. So I think you know that mod of sin x is less than or equal to mod x, or what? You know about that inequality, right? Or whatever, right? There are different ways. We know that even mod of sin x is always less than or equal to 1 also, right? So any kind of thing you can actually, you know, use some inequality to show this value is 1, right? Using epsilon delta, because you can try a couple of paths and then you arrive at, and you can see that here at, you know, in this picture, why this 0 0 there is a problem, right? Okay. So if you compare with the function sin x by x is single variable case, right? You see at origin there is a lot of wiggle, right? A similar thing happens here also, right? So basically at origin there is a problem, but actual limit exists, you can show that. Okay, then we have done couple of examples, like if the function is x square minus y square divided by x square plus y square, you know, along two different paths, along x axis and along y axis, limit is different, so this limit does not exist, right? Easy to show. So similarly we have done some other path, right? Along the line y is equal to x, okay? Now you see along x axis and y axis limit is 0, but along the line y is equal to x, limit is half. So limit does not exist, right? We go a bit further, and if the function is like this, we try y is equal to mx, and actually if this limit turns out to be a function of m, limit will never exist, right? Because, you know, it depends on m, right? Each time you change m, limit is different. But here in this case, actually, because of the factor x in the numerator, the overall thing will be 0 anyway, no matter what time you choose. So this value is 0, right? But when you take the path along x equal to y square, limit is half, so limit does not exist, right? So there are two different paths at least for which the limit is different, so limit does not exist, right? Okay. Now here in this case, you can see that you tried all different paths. Along y is equal to mx, for any m, limit is 0. Along y is equal to x square or x equal to y square, limit is 0. Then you suspect probably the limit is 0. Then you try to do some inequality business to finish the case, right? So assuming that capital L is equal to 0, look at the absolute value and show it somehow less than or equal to y. Here we have used sandwich principle because the whole thing is less than or equal to this quantity. So if you take the limit, so this portion is 0, right? Anyway, so the overall value, you know that since this is 0, okay, and x square divided by x square plus y square is less than equal to 1 because of that inequality. So it's essentially a, absolute value is less than or equal to 0 means the limit is 0, right? When xy tends towards 0, 0. Okay, so limit is done. So basically you need to remember only 3 things in the 2 variable function case. Of course, finding domain and range is straightforward. That's very common thing. Forget about it. Definition of limit of a 2 variable function. Okay, epsilon delta definition you should know. How to show that limit does not exist? So you have to just find at least 2 different paths for which limit is different, and you are done, right? Showing that the limit exists, try all different possibilities. Normally along the line y is equal to mx, along hyperbola, parabola, whatever you say, right? And if you see in a couple of cases you are getting the same limit, then you have to use inequality business to show that, right? Inequality business तो आपको आता ही है high school से, so that's okay, right? Okay, so that is how 3 चीज़ें याद रखनी है बस. अब लिमिट हो गया तो क्वांटिटी भी आसान है कि एक पोर्शन हो गया. So a function is 2 variable function is continuous at a point x comma y, I mean a comma b. If the limit exists, function is defined and these 2 things are equal. Exactly same definition as a single variable case. Because of this limit involving business, you can write everything in terms of epsilon delta also, right? Right. So yeah, so in the limit case actually I think probably I have not written, but let me just correct it if I see in the, yeah. So you note that here it is a deleted neighborhood, right? Because it may happen that the function is, we are avoiding. So generic point x comma y approaching over a comma b, where this whole thing is positive means what I am saying that the function may not be defined at a comma b, right? That example is sine of x square plus y square divided by x square plus y square, right? The function is not defined at origin, right? But still the limit exists, right? So that's why that thing you need to keep in mind. But then in the other case, so continuity means basically you can write down everything that for every epsilon positive. If you want, you can write what is the definition of epsilon delta. Epsilon delta definition of continuity of a 2 variable function. Okay, f of x comma y is continuous at a point a comma b if for every epsilon positive there exists delta positive such that mod of f of x comma y minus f of a comma b is less than epsilon whenever 0 you have to drop, whenever distance between x comma y and a comma b is less than delta. Now this distance normally we take Euclidean distance, right? Square root of x minus a whole square plus y minus b whole square, right? Got it? So you can get the definition of continuity of a function. These are some examples of functions which are continuous. A 2 variable polynomial is continuous anyway. Okay, so one can check whether this function is continuous at origin or not. So basically if this limit does not exist, the function is discontinuous, right? Or if limit exists but is not equal to the value of the function at that point, then also function is discontinuous. All these cases will be possible, right? So this function is continuous except at x equal to 0, tan inverse y by x. So one can look at any 2 variable function, right? So limit ho gaya, continuity ho gaya, right? Then we go to differentiation, right? Now you remember when we are trying to differentiate a 2 variable function, actually there are a couple of ideas that we have in single variable calculus. If y is equal to f of x is a single variable function, that function is differentiable at a point x is equal to x naught if limit x tends to x naught f of x minus f of x naught divided by exponent of x naught exists, right? This is a normal definition. You can also write in terms of epsilon delta if you want, right? So here now since we are in a 2-dimensional plane, right, I can define differentiation along x-axis, along y-axis. So basically we have two. The one is differentiation of this function partially with respect to x, We call it partially because now there, we can do it for x or y also. So this is our normal definition, right? H tends to 0, x plus h, y minus fxy divided by h, and all notations are there. Del f over del x, del over del x of f, del z over del x, f1, d1f, dx of f. All these are common notations used in different books, different kind of notations they will use, right? Similarly with respect to y. So this you can differentiate, find out easily, right? Now, you can get higher order derivatives, second order. So once you differentiate it one time, you can do it again. Now once you have differentiated with respect to x, you can also differentiate with respect to x again, or with y also, right? So f of x comma y, or f of yx, f of xy, all kind of things are you can define. So one popular question that comes, give an example of a function for which fxy is not equal to fyx. Right, a tea time problem I have given to you earlier. Give an example of a function for which the order of differentiation matters, right? Actually they are not same, so you have to give an example. Okay. So when they are equal, there is a condition. I hope you remember when they are equal. Any idea? Huh? When the partial derivative are continuous, then they are same, right? So basically all those conditions you have to, so if you have to find this kind of example, you need to look at a function for which partial derivative are not continuous at some point, and then showing something is not there, is very easy. Just find one counter example, right? Some specific case for which it is not true. Okay. So this theorem was Collins's theorem, right, which says that f is defined in some domain, and these are both continuous on D, then these are equal. Okay. And this is very important. Remember, we have used in one of the result while doing complex. Okay, then the idea of tangent plane. So there, if y is equal to f of x is a single variable function, right? Tangent, so basically derivative can be represented as a tangent at that point, right? On that line, right? Here, since it's a surface, now tangent is nothing but a plane. Everything is described in terms of plane, right? So there is a normal definition because you can write down in terms of two partial derivatives, tangent, okay? So you can clearly see the tangent plane here. Z is equal to 2x square plus y square is a tangent plane at the point x, y, z is equal to 1, 1, 3 to this elliptic paraboloid. Okay. Then just like that, in case of single variable, we have this formula that change in y variable is same thing as derivative of a times change in x variable plus epsilon times change in x. As long as, so where epsilon tends to 0, as delta x tends to 0. This definition is there. A similar definition comes from for two variable function, right? Just like the single variable, you can generalize this. Okay. So sometimes these kind of representations are useful. Okay. And then there is this result: if partial derivative exists near a point a comma b and are continuous at a comma b, then function is differentiable at a comma b. This is a condition for the differentiability of the function. Okay. So you can check couple of examples. Okay, then we have defined what is known as, so remember, now we were talking about two variable function and we are talking about differentiability of a two variable function. So along x axis, along y axis, we done partial differentiation with respect to x, partial differentiation with respect to y. But I can also define what is known as total differential, change in z. So dz, total differential, is equal to f of x dx plus f of y dy, because del z over del x. So if you see, y component is not there, it is something like change in z only, right? Because dx will cancel out, right? This notation del x is used because partial differentiation, otherwise it's the same thing as dx, right? So this dx will cancel out, you will get change in z, right? Okay, so this is the total differential. Exactly, you can generalize the definition from single variable to two variable. Similarly, for three variable. Then there are certain chain rules for differentiation. Just like that, dy by dt is equal to dy by dx times dx by dt, right? Those kind of rules are there. So we can develop the similar rules for two variable function. So if z is equal to f of x comma y, dz over dt is equal to del f over del x dx over dt plus del f over del y dy over dt, right? Now you can see, it's a fairly straightforward generalization, because if y component is not there, this is exactly the one, the rule written above, right? Just like that in the single variable case, right? So we are using this del just to differentiate, because there are two differentiations involved with respect to x and y. Everything is remain same, right? Okay, this is quite useful chain rule. Second chain rule, if z is a function of x comma y and x and y are functions of s and t, then how do we differentiate? Now, see, now when I am differentiating, I am using del z over del s, because there are two differentiation with respect to s and with respect to t. अगर single होता तो हम d use करते, right? So del z over del s is equal to exactly similar rule, right? With respect to x, then x with respect to s, plus with respect to y, y with respect to s, right? Similarly the other case, right? So this is the generalization, and you can find out the values of the second chain rule. Third chain rule is actually essentially nothing but if there is if each input, there it was x and y, here it is, say we call it x1, x2, xn, each is a function of m variables, so the whole thing can be generalized. So actually this is the complete generalized formula, right, for n case, right? So here basically, when u is a function of n variables and each variable is function of m variables, then the formula is like this, right? Normally हमने इसका एक भी इस्तेमाल नहीं किया है, हम तो two variable तक ही सीमित रखा है, but for completeness we have given this formula to you, right? Okay, then there is the idea of Jacobian comes when we do the change of variable, and this is I think we are going to use it. I think we already started about the multiple integrals. When we do the substitution and other kind of things, then we will use these kind of formulas there. So otherwise, so basically if f of xy is given and x and y are functions of s and t, from this I can find out the value of x here. So this I want to find and this I want to find, del f over del x, right? So using Cramer's rule, I think if you remember what is Cramer rules, we have used Cramer rules to find out this solution here. So these two equations were given to you and using Cramer rules we found this formula here. If j is this notation, so del f over del x is equal to 1 over j times this, and del f over del y is equal to minus 1 over j times this. This notation is nothing but, you can expand it like this. Okay, this is known as Jacobian change of variable in the Jacobian. So normally we will need it when there is a two variable integration involving f of xy and we do this kind of substitution. So the change of variable is required, right? And so we do use this formula. So dx is something, dy is something, and we will do all those kind of things. I think you will know more when we do this exactly. Okay. So if there is an implicit function f of xy is equal to 0, then dy by dx is minus del f over del x divided by del f over del y. That's a simple formula. Okay, then we talked about homogeneous function. So for example, a function like x square plus xy plus y square. So this is degree 2, this is degree 2, and this is degree 1, 1, which is 2, right? So overall function is a homogeneous function. How do we check that? We just replace x by lambda x and y by lambda y. Whatever power of lambda comes, that is the degree of the homogeneous function, right? So this function is homogeneous function of degree 2. And I think for this, there is a nice result known as, this is an example of a non-homogeneous function. So one can ask, give an example of a non-homogeneous function, right? So you can easily create one, right? Monkey saddle is a homogeneous function, right? Dog saddle is a homogeneous function. So at least 3D printer में अगर आपको dog saddle बनाना है या monkey saddle बनाना है तो आप 3D printer में ये function input दे करके बना सकते हो, right? It will come. Anyway, so this was the Euler's theorem. That's x times del f over del x plus y times del f over del y is equal to n times f, where n is the degree of the homogeneous function. Okay. Similarly, the second order result is this n minus 1 times f. Fairly straightforward thing, so I think it's easy. We can skip all this business. Then we have given the Taylor series for two variable function. So what is Taylor series? If the function is differentiable enough number of times, right, at a point, then from those derivatives I can write down. So actually, knowing the value of the function at a, derivative at a, double derivative at a, and so on, and n minus 1 derivative, etc., I can express f of x in terms of those values, right? That is a Taylor series. So now we can do the same thing in two variable functions, right? Fxy can be expressed in terms of fx, fy, fxx, fy, fxx, xy, fy, yy, right? And that formula is given to you. Yeah, so this is the formula, right? Fxy is equal to value of f at ab plus 1 over factorial 1, all differentiation with respect to x and y, single variable differentiation, evaluated at point a comma b times x minus a, y minus b, plus 1 over factorial 2 xx, this plus 2 fxy. So that means when we are writing this 2, fxy is same thing as fyx, right? That condition is automatically satisfied, otherwise it will not be valid, right? Plus rest of the things, right? And so on, you can keep on going, right? थोड़ा सा lengthy है, but मुश्किल नहीं है. And you can always see that whenever we take y component off, you get the single variable case, right? Straightforward, right? And differentiation involved by this substitution we did. Yeah, this is the important concept, directional derivative, right? So what is directional derivative? So if z is equal to f of xy is given as a surface, so normally you know that I can find partial differentiation along the x-axis or y-axis, but I want to find derivative in a given particular direction, in the direction of a vector, then how do we do that? And for that there is a formula, right? So that formula is this. Okay, so here is the formula. Yeah, directional derivative of f at point x naught y naught in the direction of u is this formula, limit h tends to 0, f of x naught plus ha comma y naught plus hb minus f of x naught y naught divided by h. Okay, and this can be simplified. I think we have given a simplification here. This is the formula. I mean the proof of this fact I am skipping right now, but yeah, this is a simple formula. Is nothing but f of x at that point times a plus f of y times b. What is ab? Component of the vector. U is a vector a comma b. In that direction I want to find directional derivative. Just compute this quantity. Okay, so fairly straightforward thing. And in fact, in terms of polar coordinates, if u can be written as cos theta sin theta, then the directional derivative formula is this, right? Just change the value and then you can get it, right? This can be further generalized to what is known as dot product of two vectors, basically, and this is known as gradient. Okay, so del f over del x times I plus del f over del y times j, one vector, dot product with ai plus bj, these two vectors, right? If you take, you get this kind of thing, right? The dot product of two vectors is this directional derivative can be described like this. So del of f is nothing but actually del f over del x times I plus del f over del y times j. this is the birth of vector calculus, and I think I have not touched too much about the vector calculus, but this is very useful for your antenna course, electromagnetic thing that you are going to do. And whole vector calculus is very beautiful actually. I think, let me see if we get time to cover couple of things sometime. It all depends. Anyway. Okay, so this much was all about two variable functions. इतना सारे में से हमको केवल 4 क्वेश्चन पूछने हैं, राइट? अभी तो ये शायद थोड़ा ही पोर्शन हुआ है, राइट? कितना आसान है तुम्हारे लिए, केवल 4 क्वेश्चन में सब समराइज हो जाएगा, राइट? Anyway, so now for complex variable functions, complex plane, you know, a plus ib, addition is different, multiplication is different. I mean, addition is same, multiplication is different. So again, there are some of these inequalities which are useful. Then some representations. I think you talked about some representations. Polar representation is very, very important because this introduces, you know, when you look at multiple valuable functions, right? The 2 and pi I term comes very, very important thing. With changing n, you are in different branch. So equation of a circle is mod of z1 is z0 is equal to r. Right? This is the radius r circle. Okay. And the distance between two complex numbers z and y is so z and z0 is said distance between z is mod of z minus z0. Okay, then argument, we have this following formula. Finding argument is not a difficult thing. This is polar coordinate. Limit of a function, again you can write down for every epsilon positive there is delta positive such that mod of fz minus w0 is less than epsilon whenever mod of z minus z0 is less than delta, and this is deleted neighborhood. Why mod here? Because distance between 2 points is mod of z minus, right? Distance is in terms of mod. Okay, so here also it is mod, there also it is mod. Okay, in the complex plane. So everything is exactly same. Here mod means, basically this mod means, you know, you are a circular disk. Neighborhood is like a circular disk, right? That is the key thing to differentiate. Everything else remains the same. Questions भी वैसे ही करे जाएंगे जैसे हम पहले करते आए हैं, right? This is the important result. A complex variable function has a limit if and only if corresponding two variable functions have limit, right? If and only if condition. I have not given you proof, and that's okay. Continuous function, again, if for every epsilon positive there is delta positive such that mod of f of z minus f of z0, because function should be defined at that point less than epsilon whenever mod of z minus z0 is less than delta. So as long as z approaches towards z0 in the neighborhood, image of z approaches towards image of z0, right? Okay, so then we have some of these differentiation you can define like this. If a function is differentiable at a point, it is continuous also at that point, right? But every continuous function is need not be differentiable. So you can easily give an example of such function. Okay, but here differentiation is a little bit more. Okay, by the way, again, I am just saying that either you look at this blue book here or this book here, right? These two books have most of the stuff given in these two books, right? Whatever we have covered. अब किताब देखने से क्या फ़ायदा? अब तो बहुत सारी चिड़िया चुग गई खेत, राइट? अभी क्या बचा है? अभी तो 2 दिन बचे हैं. बट फिर भी कुछ लोग होते हैं बिरले जो कि कम टाइम में पढ़ लेते हैं, राइट? वो बहुत ही ध्यान लगा के कंसंट्रेशन से, तो इट्स ओके. बट एनीवे, as I mentioned, Spiegel book, Lipschitz book, Sham's Outline Complex Variable is a very, very good book with a lot of examples. If you can find this book, still you can look at it for complex. Anyway, we have another important thing in the complex variable function. Limit is there, continuity is there, differentiability is there. we also have analytic function. This is something very, very important, right? What is, when we say a function f of z is analytic at a point z equal to z naught, if not only it is differentiable at z naught, but also in the neighborhood of z naught. At every point in the neighborhood, the function is differentiable. It's a stronger condition. So if a function is analytic function, obviously at a point it will be differentiable at that point. And if it is differentiable, it is continuous. Reverse is not true. So you can always give an example of a continuous function which is not differentiable. You can always give an example of a continuous function which is non-analytic. You can always give an example of a function which is differentiable but not analytic at a point. Beautiful question, tea time problems, right? We already talked about it. Okay, I think then we talked about Cauchy-Riemann equations, if you remember. If a function is analytic, it will satisfy a Cauchy-Riemann equation. What are the Cauchy-Riemann equations? Del u over del x is equal to del v over del y, and del u over del y is equal to minus del v over del x. Okay? If the function is analytic, Cauchy-Riemann equations are satisfied. If Cauchy-Riemann equations are satisfied, function may not be analytic. You need some extra condition. What is that extra condition? Can anyone tell? Suppose a function f of z is given at a point z naught, Cauchy-Riemann equations are satisfied. Can we say that the function is analytic? और क्या condition लगेगी बताओ?
Continuous partial.
Yeah, continuous partial derivatives. That condition हर जगह चल रही है, right? You remember that is very, very important condition. Okay, so that is key thing. So basically you can actually just play with the stuff, right? I can always ask questions, okay, give an example of a function which is, for which Cauchy-Riemann equations are satisfied and function is not analytic. Right? कुछ लोग सोचते हैं यार Cauchy-Riemann equation satisfy हो गया, function analytic होगा ही होगा ना, पर ऐसा नहीं है. Okay? हाँ, अगर analytic है तो Cauchy-Riemann equation satisfy करेगा. Analytic है तो उसके component function harmonic function होंगे. U and VR will satisfy del square u is equal to 0 and del square v is equal to 0. Right? Laplace equation को satisfy करेंगे. Let us do one or two examples actually. Let us do one or two more examples on analytic functions, okay? Suppose f of z is equal to uxy plus I times vxy and its conjugate function f of z bar is equal to uxy minus I times vxy. Both are analytic. In domain D. Then can you show that f of z must be a constant function? Function f of z is given u plus iv, analytic है. f z is an analytic function such that इसका complex conjugate is also analytic. Means u minus iv is also analytic. Then the function must be a constant function. How will you show that? चूंकि fz analytic है, fz bar analytic है, both will satisfy Cauchy-Riemann equation. Just try to start with there and see what happens. From the first one we will have del u over del x is equal to del v over del y and del u over del y is equal to minus del v over del x, right? Because this is one set of equation, and from here suppose this is capital U and this is capital V, basically minus of this is capital V, right? So I am saying capital V is equal to minus of I or whatever, right? Minus V fxy. Okay, so then we have ux is equal to vy, this is capital, and uy is equal to minus Vx. Second set of equation, right? हमने क्या किया है, स्मॉल यू एक्स वाई को कैपिटल यू मान लिया और माइनस वी एक्स वाई को कैपिटल वी मान लिया, राइट? सो दैट आई कैन अप्लाई द कॉची-रीमान इक्वेशन. सेटिस्फाई करेगा ये भी, बिकॉज एफ जेड बार इज ऑल्सो एनालिटिक, राइट? सो आई कैन जस्ट सब्स्टिट्यूट द वैल्यू एंड सी व्हाट यू गेट. So this implies that you will get ux is equal to minus vy and uy is equal to vx. I would say it's the third one. Now combining first one and third one, you can see that we will get ux is equal to 0. And this will also imply that Vx is equal to 0. This implies that f dash of z will be what? Ux plus I times Vx is equal to 0. So if derivative of the function is 0, then fz must be a constant function. Right? सिंपल इस तरह के मॉडिफिकेशन हम 50 कर सकते हैं, राइट? एफ जेड इज एनालिटिक, एफ जेड बार इज एनालिटिक, शो दैट फंक्शन इज कांस्टेंट, राइट? अनदर वन आई कैन गिव इट टू यू. सपोज एफ ऑफ जेड इज एनालिटिक फंक्शन, ओके, एंड mod of f of z is constant. Show that f of z is a constant function. कैसे करेंगे? f of z is suppose u plus iv, right? एनालिटिक फंक्शन है, of course some domain में, right? It will satisfy Cauchy-Riemann equation. Del u over del x is equal to del v over del y, and del u over del y is equal to minus del v over del x. Now it is given that mod of f of z is a constant function. ये equation 1 हो गई. So mod of f of z क्या होगा? Square root of u square plus v square, right? And this is a constant function c. This implies that we will have u square plus v square is equal to c square. We can differentiate it. With respect to x हम करेंगे तो क्या मिलेगा? 2u del u over del x plus 2v del v over del x is equal to 0. Cauchy-Riemann equation को यहाँ पे इस्तेमाल करेंगे तो what you will get? करो, खुद भी तो कुछ करो यार, मैं ये सब करूं. 0 आएगा ना? Got it? So ux is equal to 0 and vx is equal to 0, and hence actually function is a constant function, right? Right? Getting? Either ux is 0 or u square plus v square is equal to 0, right? U square plus v square is equal to 0 means anyway, you know, that 0 function, right? So I think in either case you are getting a constant function, right? हो गया ना आसानी से? ऐसे 50 क्वेश्चन बनाए जा सकते हैं, राइट? छोटे छोटे मॉडिफिकेशन करके, राइट? हम तो ऐसे तुमको कुछ सैंपल करा दे रहे हैं, राइट? इसके आके कितने लोग नहीं कर पा रहे हैं, उनको समझ नहीं आ रहा है. कितने लोगों को समझ में आ गया एक्चुअली ये सब? ओके, काफ़ी लोगों को समझ में आया, कुछ लोग अभी भी मोबाइल पे लगे हुए पीछे. एनीवे, okay, so basically if the function is analytic, it will satisfy Cauchy-Riemann equation, and then you can, depending upon the condition, you can see what has to be done there, right? That can be taken care of. Okay, हम कहाँ पे थे? Okay. Okay, harmonic function is an important thing. So if fz is analytic, component function u and v will be harmonic. Means they will satisfy this thing, that del square over del x square of u plus del square over del y square of u is equal to 0. Means u is a harmonic function, v is a harmonic function, right? That is a condition. And I think harmonic conjugate, I think we have done this. So we know that if f of z is analytic, then u and v are harmonic functions. Suppose by chance you are able to find a real function u x y which is harmonic, means del square u is equal to 0. If you can find another function v such that v is harmonic and it satisfies Cauchy-Riemann equation, then v is known as harmonic conjugate of u, right? And I think there is a, so I have shown you, if f of z is analytic, if and only v is a harmonic conjugate of u. Okay, I think this I have done. Yeah, if u is something like this, find harmonic conjugate of u. So u harmonic conjugate has, basically u is harmonic, we need to find v, just substitute. So we know that if f is analytic, it will satisfy Cauchy-Riemann equation. You just substitute. So from here, u is given, v is unknown. You can find v from Cauchy-Riemann equations, right? So vy is equal to this. When you integrate with respect to y, keeping x constant, so constant can come as a function of x, because if you differentiate x, it will go to 0, right? So vy is this. From there you can find, again by using the other equation, simplify, you can find what is the value of phi x. Phi x turns out to be 3 phi x cube plus c. Phi x is known, so my v is known, and hence u is known, and so you can find the analytic function u plus iv, right? If u is given, you can find v by solving Cauchy-Riemann equations, right? इतना ही तो है, और कुछ करना नहीं, simple calculations, right? And once u and v is known, so you know the function f of z. Okay, elementary functions की बात हमने बहुत सारी करी. Main चीज़ है, there are multiple valued functions like log. Log is a multiple valued function, and I think if you see the picture, this is the Riemann surface of the log z function. For each n there is a branch. Okay, all these multiple valued functions are analytic on one of the branch. Otherwise, they have a singularity. Like for example, in log z, origin is a singularity known as branch point. Okay. Similarly, square root of z we have done. Square root of z, right? There are two branches. You saw that, right? Origin is a branch point here also. All branch points are singular points. Branch points are points which are common to all surfaces, right? All branches. Then we talked about trigonometric function and so on and so forth. ये तो तुम्हारा $1 million वाली problem थी, which you can anyway do it if you enjoy. इस पे मेरा ज़्यादा मन है. जिसने ये कर लिया उसको तो ये डबल ए पक्का ही है, right? उसको $1 million भी मिलेगा, वो ज़्यादा अच्छा है. ये फालतू का एग्जाम देके क्या करोगे, right? शायद तुम में से कोई कुछ कर पाएगा इसके लिए. There is a nice book in the library, Riemann zeta function, you can read it. Anyway, singular point, isolated singularity, जिसके neighborhood में कोई और singularity नहीं, वो isolated singularity, right? Poles, normally at poles function is unbounded, so it fails to be analytic at that point, right? So square root of z minus 3, z is equal to 3 is a branch point, right? Removable singularity, अगर हम उसको function को redefine कर सकें तो removable singularity, in this case for example limit exists कर रही है, right? So we can redefine the function. Essential singularity, which is not a pole, branch point or whatever, or neither removables, then that is essential singularity, like this e raised to the power z minus 3. हो गया, बाकी और क्या, ये तो हमने डिफाइन किया था ना लाइन इंटीग्रल, ये डेफिनेशन है लाइन इंटीग्रल अलोंग कर्व्स इफ़ यू कैन डू द पैरामीट्रिक थिंग। आई थिंक आपको याद होगा मैंने प्रश्न पूछा था यहाँ पे कि गिव एन एग्जाम्पल ऑफ ए कर्व विच यू कैन नॉट फाइंड ए पैरामीट्रिक इक्वेशन, शायद तुम लोगों ने किया होगा। लाइन इंटीग्रल अलोंग ए प्लेन, ये तीन सम फाइंड आउट करके लाइन इंटीग्रल ऑफ जी अलोंग सी विद रिस्पेक्ट टू एक्स, with respect to y and with respect to arc length, right? And there are formulas to compute this, ये तो सब आसान काम है, right? हो गया बस, I think that's all. So wish you all good luck for the exam. 4 क्वेश्चन है, आराम से पूरा आराम से सो करके आना और then you will be able to do it, right? 8 घंटे की नींद लेकर के आना, लास्ट मिनट में मत जगना, okay? Thank you.